toxic.
These are not toxic relationships. No, we're going to talk about relationships. Relationships involving the heats of reaction. So heat of reaction is an extensive property. It depends on the amount, right? So if we take a chemical reaction like carbon and oxygen reacting to form carbon dioxide, 1 mole reacting with 1 mole would give off 393.5 kilojoules of energy. If we did 2 moles, how much energy? Double, twice as much. So you double the amount of stuff reacting, you double the energy. So if you multiply the coefficients in the equation by a number, then you have to multiply the heat of reaction by that same number. Does that make sense? If we run the reaction in reverse, we take carbon dioxide and decompose it into carbon and oxygen. That's a little hard to picture, but let's think about an ice cube. So when you melt an ice cube, you have to put a certain amount of energy into it, right? If you take that melted ice cube and you want to freeze it again, how much energy do you have to pull out? The same amount, right? You can't lose or gain energy by just doing physical transformations like that. Same thing with chemical reactions. This reaction in the forward direction released 393.5 kilojoules. If we want to run it backwards, we have to put 393.5 kilojoules of energy back into it. So when you change the direction of the reaction, you change the sign on delta H. Delta H is a state function. How you get there doesn't matter. So if we can express this reaction as a series of steps, even if those steps can't possibly result in what we want, but we can still express them, then we can find the overall reaction by just looking at the sum of the individual steps. So let's take that out of chemistry and maybe look at a staircase. So I'll just make it a little different than yesterday. Yesterday it was feet. Today it's going to be meters. 2 meters, 1 meter, and 1 meter. So if you want to go from the ground up here, the difference in height is 4 meters. Didn't mean to do that. 4 meters. You could go directly from the ground up to there, a big leap. The change in height would be 4 meters. Or you could go this way and go up 1, go up another, and then this last step is twice as big. So this difference is 1 meter plus 1 meter plus 2 meters. It's the same. Doesn't matter how you got there. You okay with that? Same thing applies for chemical reactions. Actually, this would be faster. So what we're looking at here is an overall reaction of A plus 2B going to form 2D. But we could envision that as like going up steps instead of just making the leap. We could go A plus 2B making C, and then the C reacting to form 2D. So instead of going directly to the product, there's something in the middle that gets made, and then that reacts and forms the ultimate product. The energy change is the same. It doesn't matter how you got there. So the one we're interested in is going from A plus 2B down to 2D. But we could get there by first going up in enthalpy to C and then coming down to 2D. The difference is the same. This change is equal to this change plus that change. You okay with that? If we look at the chemical equations, we can add them much like you would add math equations. So when we're forming the C, does the C hang around? Is it present at the end? No, because there's another reaction that eats it up. And so we have C on both sides. We can cross those out. We write down what's left. This is our overall reaction. So what we can do, and this is what Hess's law tells us, is if we can write stepwise reactions that together add up to the overall one that we're interested in, we can just add up the delta H's for each of the individual ones and get the final result. So this one, going to C delta H, that was delta H1, and this was delta H2. So this one, I don't know where the E came from. Delta H3 equals delta H1 plus delta H2. Any questions? It's going to get much messier. So Hess's law says the change in enthalpy for a stepwise process is the sum of the enthalpy changes of the steps. So here's a Hess's law problem. It says find the heat of reaction for N2O plus NO2, giving us 3NO. And it says use these reactions with known heats of reaction. So we have these three reactions where we know what the heat of reaction is. We're trying to find the heat of reaction for this. We have to figure out how we can combine these reactions so that when we add them up, we get this. There's not one set way to do this. It's a little like balancing equations. You could come at it in different ways. What I like to do is I look, it'll be interesting to see if I do this different than I did it yesterday. I'll look at these and, okay, these are the reactants and this is the product. I need one of these that's going to give me the product, right? I want NO as a product. So if I look at this first reaction, NO's a reactant. Well, I don't want NO over here. I want NO over there. What else do I have going on here? O2, that's not anywhere in there. NO2, that's a reactant. So if I take this reaction and I flip it backwards, then I've got a reactant and a product in the correct place. Let's try it over here. So I can write this one backwards. Yeah, pick a pen. 2, NO2. I'm going to leave the state symbols off. They're not important in this example. Sometimes they are, but they're not important on this one. Pay attention. So I'm writing the product and then the reactants. So when I switch it backwards like that, what do I have to do to delta H? I have to change the sign. So I'm going to make it positive. It was negative. I'm going to make it positive. So I'm making progress, but I still don't have things taken care of. Well, let's see. This one, well, let's just look at the second one. Do I want to put this one in as it's written, or would I want to flip it backwards? I want to keep it because this is the product over here, and this is, well, those aren't either, but maybe they'll work out. They will. So N2 plus O2 going to 2NO. Do I need to do anything to delta H? No, it's okay. And let's look at this last one. Well, this is a reactant, and these, N2 and O2, those are these pesky guys that are present here that I want to get rid of, because they don't show up in the overall reaction. So I need to use them up somehow. So I'm going to just copy this equation down as written also. 2N2O going to 2N2 plus O2. Well, this is a reactant, so I want to keep that on the reactant side. And then these guys, I'm just like, well, I need to get rid of these. So here's an N2. I need N2 over here on the product side. And I've got O2, and I need O2 on the product side. I've also got O2 up here, so I've got a lot of O2 going on. I need to make them come out even. And this is where it gets a little tricky sometimes. Here I've got one nitrogen, here I've got two nitrogens. There's oxygens all over the place. I'm going to see if they'll take care of themselves if I deal with the nitrogen. So two nitrogens, if I multiply this whole equation by 2, then I could get two nitrogens there, and that would cancel out the other nitrogens. So what I'm doing here is I'm taking this whole thing times 2. So when I do that, let's use a different color. I have to multiply the delta H by 2, and I multiply both of the reactants by 2 and this product by 2. Delta H doubles because if you have twice as much stuff reacting, delta H will be twice as big. Well, now this N2 and N2 over there, I've got two nitrogens. These two nitrogens as reactants get used up. These were two nitrogens that got produced from this reaction. They get used up. The order of these doesn't matter. This is not the order in which they would happen. It just happens to line up with this. I have two oxygens here, and I have two oxygens on the other side, and so I can cross those off as well. So I got rid of all the things that don't actually show up in this equation. Now let's take all of this and copy it down and see what I have to deal with.
So you can cancel O2s because you have the same numbers of, got it, okay, so you're balancing at the arrows.
I'm balancing at the arrows, so it's like
each other and all three at the same time. Does that make sense?
Mm-hmm. So if you took two math equations and added them together, you would add the left sides and the right sides. And so what you'd end up with here is A plus B plus C equals C plus D plus E. You'd say, well, if I subtract C from both sides, those go away. It's the same idea. So I'm going to write down what I've got. I've got 2 N2O, and I've got 2 NO2. I'm keeping my arrows lined up because that makes it easier to look at. And then over on this side, how many NOs do I have? 6. That's one of my favorite compounds. No! This is 6 no's, one for each kid. No, 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 no! Then I have to add these up. I didn't leave myself much space. So adding up the delta H's, I've got positive 113 because I flipped that one around. And then I'm going to add 2 times 182.6 plus negative 163.2. So delta H is 315.1 kilojoules. This is delta H for this reaction. Is this reaction the same as that one? No. What's different about it? The coefficients are all doubled. So I just need to divide by 2. So if I divide all the coefficients by 2, what do I have to do to delta H? I have to divide by 2. So we're dividing everything by 2. Bless you. So this is divide by 2, divide by 2, divide by 2. So now my coefficients are going to match up 1, 1, and 3. And so this is going to be 315 divided by 2. So delta H for that reaction is going to be 157.6 kilojoules. So it still have the 1 decimal place, so I rounded it. Any questions?